All right, 3-4-day-2 is where we are at. We're still solving, but we're switching gears slightly to solve not exponential equations, but logarithmic equations. So the first two that I want to have us look at are really, really simple ones because I want to focus on this new step that we have to add. And it actually makes a lot of sense when you think about what we've talked about with logs and exponents being inverses. Okay, we saw yesterday, or in the last lesson I should say, maybe you watched it yesterday, that to get rid of an exponent we had to use a logarithm. Okay, and we've emphasized the entire unit that exponents and logs are inverses. Okay, so now we're faced with this situation where we have a logarithm and we have to get rid of it. Notice on the left side of this equation there's just a natural log of x equals 3, and I need to get that x by itself. Here's the way we do it. Okay, a natural log has base e, so I would rewrite this equation like that. Okay, I turned both sides into exponents that are base e, which seems like kind of a strange thing to do, and maybe you're thinking, why would you do that? Because an exponent that is base e and a log that is base e will cancel. We have x by itself, and we just need to evaluate e to the third power on a calculator, which is 20.09. Let's see another one that's real similar. ln of x is 2. Okay, really, really similar. Write each side as an exponent. And the problems we'll see, it's not always going to be base e. That's worth pointing out at this point, that I'm only using base e because the problem started with a natural log. Okay, the power that I use, or the base I use, that all just depends on what log we have. I mean, that one should look basically identical to the first one, except it equaled 2 instead of 3. Okay? The ones we'll get to here in a little bit, really on the next slide, we'll come back to ones like that with a few extra steps. There are, however, a couple different ones I want to show you. Like an example C, what if you have something like log of 3, log base 3 I should say, of 5x minus 1, and that equals log base 3 of x plus 7. Notice we have one logarithm on each side. They are both base 3. This is the case where you can just simply drop the logarithms and you could continue to solve without them. That was one of our properties that we saw a little while ago. Might need to talk about that one again, but that's the case. I think it was property number 4. We had 7 total, and that was number 4. Okay, from there, I mean, it's a matter of solving, but you know what we have left over is not really terrible to solve. I could add 1 to both sides, subtract x, divide by 4. None of this involves exponents or logarithms because we got rid of them. And then we'd see that x is 2. Okay. Now, take a look at this one. This is a good one to do right after, because this one is typically more often a source of some possible mistakes. Let's say we've got log base 6. This whole problem is going to be in base 6. And you're noticing all the ones that we're solving, I haven't had to change bases. That might have been something you were wondering about, that, you know, on all these, if we have multiple logarithms, they're all the same base. Could you have expressions where the bases are different? And you can. That can certainly come up. They are a lot harder to solve. And we don't do anything other than like some of the basics with the change of base formula that we saw in the first day. That's about all we do with changing bases. All right, how about something like that? It kind of looks like the one before, except we have 2 log base 6s on the left side, which kind of raises the question, can we just cancel all 3? Unfortunately, the answer is no, we can't. We can only do it when we have 1 on each side. However, this is a case where condensing is going to be really helpful. I can condense it over division. And this is now the point where I get it down to 1 log base 6 on each side. Okay, which would give us 3x plus 4 equals 10x, and then 4 equals 7x, and finally x would be 4 over 7. Okay? Good one to see there, where you have to condense the left side to get those to come together. Okay? We have 2 more to go here. Here's how I'm going to set up the space that we have. But what I was saying when I was explaining before I did that one, that one tends to be perhaps the source of some more mistakes. The mistake is to drop all 3 log base 6s before you condense. I don't know if I emphasized that enough. That's something you got to be careful. That if you see that left side needs to be condensed before you could drop them. Because if you were to do it without doing that, you would see that you wouldn't get a solution of 4 over 7. 5 plus 2 ln x equals 4. Okay, just one natural log. It's on the left side. This is not like the last 2. Okay, nothing's going to drop here. It's going to look a little bit more like the first 2. So I subtract 1. Excuse me, I subtract 5 and I get -1. And then I divide by 2. And now at this point, it's starting to look a lot like the first 2 that we did. Okay, notice the left side is just ln of x. That's a case to use base e. And again, we're left going to the calculator to evaluate e to the -1/2 power, which is about 0.607. Okay? That is more typical as opposed to the first 2. Like, it uses that same step that we have to rewrite the expression with both sides that are exponents base e, but it's got a few extra steps along the way. And that's typically what you'll see. Okay, how about this one? 2 log base 5 of 3x equals 4. Okay, I like this one that it's not base e. Okay, we'll deal with that when we get there. But this is base 5. But I'd start by dividing both sides by 2, and we'd get to there. And now we kind of have a little decision that we need to make. Do we first have to deal with log base 5, or could we divide by 3 and deal with the 3x? Okay. Eventually we will divide by 3, but we have to get rid of the log first. But notice here, I'm just sticking with whatever base I have. This isn't e, this is 5. The exponent and the log cancels, and we get to something that's pretty doable to solve at this point. 3x equals 25. And dividing both sides by 3. You could leave your answer as 25 over 3, or like decimals, you could go 8.3 repeating. Okay? So the one extra element that one has is after we did kind of the key step of rewriting it as an exponent that's base 5, we still had to divide by 3. Okay? The big difference there, notice that inside the logarithm, we had a 3x. Here we just had an x, so after we rewrote it as an exponent, there was nothing else to do, and this one we did. All right, one more application. Okay, notice the graph down there, which I want to point that out. You can see why it's appropriate to have logarithmic models, because they model different type of, like a different type of a rate of change. Okay, you can notice here that it looks like this list is growing quickly at first, and it's starting to slow down as time increases. Okay, that's very often a situation where an expression with a logarithm is going to fit the data best and give you the most accurate model. Okay, this is a endangered species list from, I think this was a mistake here. I believe this should say 2010 to 2022 is what it should say. Okay, 2010 to 2022. It would look something like this. We want to find out when is that endangered species list going to hit 360. Which is asking us to solve that. Okay, when is this expression right here, because that as time changes, that gives you the prediction of how many endangered species are going to be on the list. When is that going to equal 360? Your first step would be to add 119. Which would give you that. Second step would be to divide by 164. A lot of you would probably just write that as a decimal at that point. I don't want the rounding error, so I'm going to leave it. Plus, I like to go to my calculator just at one time at the end. Notice on the right side, nothing but natural log of t. Now we're right where we need to be. There's t. And it leaves us at a point where we need to go over to our calculator and evaluate e to the 479 over 164th power. If that expression isn't just made for a calculator, I don't know what is. You would see it's about 18.55. Okay. So now to look at the years, I would say somewhere between 2018 and 2019, you'd expect that list to hit 360 endangered species.